Okay, so today we were talking about limits of rational and piecewise functions. So just to remind you what those two are. Rational function, what it looks like on paper is a fraction. So this right here is a rational function. And then a piecewise function, you know what piecewise functions look like. This is a piecewise function, right? So right here, okay? So we are going to be looking at finding limits of those two, okay? So these are going to be functions that agree at all but one point. So let C be real numbers and let f of x be equal to g of x for all x values not equal to c, an open interval containing c. If the limit of g of x as x approaches c exists, then the limit of f of x also exists, and the limit as x approaches c of f of x must be equal to the limit as x approaches c of g of x. So let's see what that means, right? All right, so it says find the limit analytically. So just like 2 days ago notes, okay? So we are going to say, all right, I'm going to use direct substitution to plug in 2. So we're going to do 2 squared plus 2 minus 6 divided by 2 minus 2. So numerator, let's not do that first. Let's do the denominator first. Let's do the denominator 0. That's not okay, because it doesn't matter what I get in my numerator, I can't divide by 0. But let's see what we get in our numerator. We get 4 plus 2 minus 6, which is also 0. Having a 0 in your numerator is okay. This is not okay. So if I had 0 over 26, then limit 0. But 0 over 0, not okay. This is undefined. So does that mean the limit does not exist? No, it doesn't. Okay? It does not mean the limit does not exist necessarily. So we now have to find another way. Okay? So if I just showed you this rational and I said, is there something you can do with it? Hopefully you'd say, oh wait, you can factor it to see if it's simplifiable. So that's what you should always be checking with rationals, is if first you try plugging in that value if you're trying to find the limit, that c value. If it doesn't work, meaning you get a 0 in the denominator, then you're going to have to try to factor it and simplify it. Okay, so let's do that. So we're going to do the limit as x approaches 2. You can't stop writing this until you actually plug in 2. So this has to be there until you plug in 2, and people will like not write it, and it's just not proper. Okay, so x squared plus x minus 6 factors to x plus 3 times x minus 2. And then I have over x minus 2. Is this simplifiable? Yes. X minus 2 divided by x minus 2 is 1, so that cancels. So this is equivalent to the limit as x approaches 2 of x plus 3. Can I solve that analytically? Can I solve that using direct substitution? 2 plus 3 is 5. So the limit is 5, okay? Let's think about why the limit is 5, okay? So let's look into graphing this here so you can see why. All right, so if I were to graph this, okay, a rational function, remember the first thing you graph is a hole, if there are any. Are there any holes in the graph? Yes. Where is the hole if x minus 2 canceled out? Well, it's at 2 comma. And then remember, I have to plug in 2 into the new simplified function, so I'm going to plug it in there. I get 5. That means there's a hole at 2, 5. So let's graph the hole, 2, 5. And then we can graph the line y equals x plus 3 to see what the rest of the graph looks like. So y-intercept of 3, slope of 1. You can see that it would have gone through that point if there wasn't a hole there. Okay, let's do my best here to make a straight line. Come on. It's good enough. Okay, so now if you look at the limit here, I shouldn't have done that because we all know why, right? I went through the hole. It's saying that there's a point there. I got to do this again. Straight. Look at that. Much better. Ooh, that's not very straight. Okay, so that's what it looks like, right? Now, if you look at the limit as x approaches 2 from the left, you're approaching 5. If you look at x approaches 2 from the right, you're approaching 5. So the limit is 5, right? So that is the case there where the limit does exist. and there's a hole, right? And that'll always be true. Okay, next. What we're doing here is called the cancellation technique. Okay, so what we're going to do is we're going to go through each problem. Let me look ahead here. At any point, you can, actually, you know what? We'll do the first two together, and then the practice you can pause and try on your own. Okay, so first thing we're going to do is we're going to try direct substitution. Since this looks like a fraction, meaning since it's irrational, I'm going to plug 2 in the denominator first. If I get 0, then I know that I have to try the cancellation technique, which is factoring and simplifying it. Okay, so if I plug in 2 in the denominator, I get 0. So I can't use direct substitution. So now I'm going to factor this. So I'm going to do limit as x approaches 2 of, and I'm going to factor the numerator and the denominator. So my numerator, I need two numbers that multiply to give me -2 and add to give me 1. X minus 2 and x plus 1. And then now my denominator is a difference of squares. So 2 sets of parentheses. Remember, one's plus, one's minus. The square root of this number has to go first. People like to change this to x plus 2, x minus 2, which is wrong. So it's 2 plus x, 2 minus x. All right, now I want to look to see if anything cancels out. Okay, so people right away, they'll say like these cancel out. That is not true. Okay, so x minus 2 and 2 minus x are not the same thing because 5 minus 2 and 2 minus 5 aren't the same thing. Okay, but think about plugging in 5 there. Think about plugging any number you want in there. I like 5. So I'm going to do, if I plugged in 5 minus 2, I get 3. And if I plug in 2 and then do minus 5, I get -3. So this doesn't cancel and simplify to 1, all right? Or it doesn't simplify to 1, which we call cancel out. This simplifies to -1. These are opposites of each other. This is a positive x, this is a negative x. This is a -2, this is a positive 2. So these are opposites. Anything divided by its opposite is -1, so that cancels to -1. Okay, so now I have the limit as x approaches 2 of -1 times x plus 1 all over 2 plus x. So now I'm going to retry direct substitution. If I plug in 2 in the denominator, now I don't get 0, so I'm good. So I have -1 times the quantity of 2 plus 1 over 2 plus 2. So that is through -3 over 4. So the limit is -3/4. All right, let's look at another one here. All right, so if I plug in -2 right now, I get a 0 in the denominator, so I can't use direct substitution right away. So I'm going to use cancellation technique, aka I'm going to factor and simplify. So I have the limit as x approaches -2. Notice I keep writing that until I can plug in -2. All right, I need to factor 2x squared plus 7x plus 6. So I'm looking for two numbers that multiply to give me 12 and add to give me 7, which are 4 and 3. Don't forget to divide by your lead coefficient, which is 2, and simplify your fractions. This is 2 over 1. So I get x plus 1 times 2x plus 3. If you factor a different way, then factor your way, right? Just showing you the way that I factor with my class. And then x plus 2 in the denominator. Okay, so I wrote x plus 1. This was supposed to be x plus 2. My bad. Right here, this is x plus 2, right? This is 2x plus 3. Okay, now I can simplify this. X plus 2 and x plus 2 cancel out, hence the name cancellation technique. Limit as x approaches -2 of 2x plus 3. And then now I can plug in -2. So 2 times -2 plus 3 is -1. So the limit is -1. Okay. So basically, if you think about what you're doing here, you're doing all the steps to find the y value of the whole, right? Because that's the limit. All right, go ahead and pause the video and try these two and then come back and see how you did. All right, direct substitution, if I plug in a 3 in the denominator, I get 0, so that's not going to work. So I need to try to simplify this. So this is x plus 4 times x minus 3 over x minus 3. X minus 3's cancel. The limit as x approaches 3 of x plus 4. Plug in a 3 and I get 7. This one right here, try plugging in the 2 in the denominator. I get 4 plus 14 plus 6, which is not 0. So I do not have to use the cancellation method here, cancellation technique. I'm going to plug in 2. So if you did use the cancellation technique by factoring the numerator, factoring the denominator, it's fine. It's just you did more work. So this is 4. 2 times 4 is 8, minus 2 is 6. And then this is 4. This is 14. So that's 18 plus 6 is 24. And then 6 goes into both of those 1 time, 4 times. Right? Okay. Practice with piecewise functions. So first we're going to do it graphically, which you have been taught before, but I just want to make sure everyone's okay with it still. So piecewise functions, as a reminder, are often more complex. They involve 2 or more graphs within different parts of the domain. Limits where the domain splits will exist only if the graph approaches the same number, same y value from the left and the right. So remember, recall from yesterday, limits do not exist at which 3 things? Jump, asymptote, oscillating behavior. This graph has no oscillating behavior. It does, however, have jumps, right? So I can see right here the limit doesn't exist at -1. Limit doesn't exist at +1. Anywhere else? No. Right? Actually, it's like this, right? Okay. So the limit doesn't exist at +1 or -1. Even before I start, I know that, okay? All right, let's go ahead and do these. The limit as x approaches -3. So we're going to go to -3, and we're going to approach -3 from the left and from the right. So approach -3 from the left, approach -3 from the right. I'm approaching the same y value, which is -1. All right, now we're going to do the limit as x approaches -1. So where's -1? Right here. So we're going to approach -1 from the left. We're going to approach -1 from the right, and we're approaching 2 different y values. This is 1, and this is 2. So here the limit does not exist. All right, next one, the limit as x approaches 1. Approach 1 from the left, approach 1 from the right, and you're approaching 2 different y values once again, so the limit does not exist. All right, next one, the limit as x approaches 2. The limit as x approaches 2. So approach 2 from the left, I'm approaching the y value of 1. Approach 2 from the right, I'm approaching the y value of 1. So the limit does exist, and it is 1. Last one, the limit as x approaches 3. So here's 3, approach 3 from the left, approach 3 from the right. I'm approaching the same y value, which is right here, which is 0. So the limit as x approaches 3 is 0. All right, so that's a refresher on how to do limits. So how do we do this graphically? Or sorry, how do we do this analytically? So if a graph's not provided, we need to check the left and right-hand limits to see if they agree algebraically, right? So if I want to know if the limit as x approaches -1 exists, I checked it from the left and I checked it from the right, and I got 2 different y values, right? So it did not exist. Here, I checked it from the left, I checked it, or at 2, you can't see what I'm touching. I checked it at 2, from the left and from the right. I got the same y value, so the limit did exist, and it was that y value, which is 1. So if I want to know the limit, if the limit as x approaches 1 exists in a piecewise function, I'm going to have to plug in 1 into this part and this part and see what 2 y values I get. Okay, I'll try to explain it off to the side graphically what you end up getting. Okay, so we're going to plug in 1 into we're going to find the left-hand limit first. So we're going to say the limit as x approaches 1 from the left, and that's of x cubed plus 1. We're going to plug in 1. So if I plug in 1, 1 cubed is 1 plus 1 is 2. So basically, you have a point at 1, 2, right? So like, let's say that's the point 1, 2, and it's closed because of this, okay? The limit as x approaches 1 from the right of, and now I'm going to plug it into this function, x plus 1. Plug in 1 there, I get 1 plus 1, which is 2. So I'm approaching this way, and then I'm also approaching 1, 2 from this way. So I'm approaching the same exact y value. That means the limit does exist, and it's 2. So the limit as x approaches 1 of, we'll just call it the function f of x instead of, we'll say that this whole function right here is f of x, is equal to 2. Okay, so we're going to do the same thing here. This time we're going to directly substitute into 3 into each equation. So let's find the left-hand limit. The limit as x approaches 3 from the left of 1/3 x minus 4. All right, so we're going to plug in 3. If we plug in 3, 1/3 times 3 is 1. 1 minus 4 is negative 3. Here, limit as x approaches 3 from the right. We're going to plug in 3 into the second equation, which is 2x plus 5. So plug in 3 there, you get negative 6 plus 5, which is negative 1. So basically, if you think about what this looks like, clearly the limit does not exist, but you have a point at 3, negative 3 that's closed, and then you have a point at 3, negative 1, which is open. So what you have is a jump. So you have something that like looks, that's a line, oops, that's going up, and then there's a line going down like this. So it looks something like this, and there's a jump in the graph. So the limit does not exist here. So the limit as x approaches 3 of this function, which once again I'll just call f of x, it does not exist. All right, last part is just double checking that you understood from last semester and now how to find limits graphically. So go ahead and pause the video and find these 5, and then come back and check. Limit as x approaches negative 2, approach it from the left, approach it from the right. It's the same y value, negative 4. 0, approach it from the left, approach it from the right. It's the same y value, 3 point something. Let's say 3.5. Limit as x approaches 1, approach it from the left, approach it from the right. You're approaching 2 different y values. The limit does not exist. Also, I can see there's a jump there, so I know it. All right, d, the limit as x approaches 3, approach it from the left, approach it from the right. You're approaching the same y value, which is 2. Last one, the limit as x approaches 4, approach it from the left, approach it from the right. Does not exist. 2 different y values. There's a jump in the graph. Okay, so that's it for today. Go ahead and get started on your homework. Your homework will not just have this stuff on it, but it'll also have finding it by direct substitution. So make sure that if it says find the limit, always try direct substitution first. If direct substitution doesn't work, then go ahead and try the cancellation technique, which means factor and simplify, then use direct substitution.